Okay, so this is a supplementary session to help people who may not be too familiar with linear systems come up to speed. So to make this session useful, feel free to ask questions as they arise. There will be some sort of questions we'll ask you just to consolidate your learning as we go on. So here are the learning objectives. So we're going to go over an impulse response and talk about why it's useful. We're going to talk about how to expand a signal in terms of weighted and shifted delta functions, describe and apply the definition of a linear system, describe the superposition principle, describe and apply the definition of shift invariance, talk about how convolution relates to the input and output of a linear shift invariant system via the impulse response, compute the convolution of an arbitrary function with a shifted delta function, compute the convolution of two rect functions, and develop an intuitive understanding of what 2D convolution is like, similar to your MATLAB homework assignment that's due later today. So the first thing we're going to do is review, and some of this will be review of material that Professor McVeigh covered in his lecture. And so we'll be basically reviewing the material, sometimes extending it, sometimes taking a slightly different view of it. So the intuition behind an impulse response is as follows. Imagine you have the object, let's say this is the object here, okay, which has two dots, all right? And so there's dot one and dot two, and that's what you'd like to make an image of. And then what you get is you run it through your system, and then through your system, you get a blurred image. Okay, so now these two dots have gotten blurred out. And the idea is that the impulse response is essentially the response to one dot. So for example, the system, the green dot goes through and gives you that green image, and the pink dot goes through and gives you that pink image. And then what we want to say is that the overall image is just the sum of those two blurred images. Okay, so the idea is that we can think of the input as a weighted sum of these impulses. So this input here is just two impulses. Then the response is just a linear sum of the two responses. So these are some examples here where we have, here we have our point stimulus, and this would be PSF, which stands for point spread function. Okay, so that's just another term for impulse response. And so in some cases, you can just use a wire, a very thin wire, and look at the impulse response. I think in lecture, Professor McVeigh said that sometimes they just use the head of a ballpoint pen. So just a little tiny object, and you're just looking at sort of here, this is this very, if we look at this sort of in cross-section, it'd be a little dot. And then if we look at this in cross-section, it would be blurred out into the contours of that Gaussian response. Okay, so first thing we're going to do is we're going to review how we define that impulse response. And the key is we use what's called a Dirac delta function. The notation is as follows. Typically in this class, we'll be using either 1D or 2D. And the notation is simply delta of x or delta x of y. So we'll tend to use these notations. And if you're doing your project in, say, 3D or doing something, then you'd have x, y, and z. Since it's just a mathematical object, you can obviously go to n dimensionals or infinite dimensions. But for this class, we'll just really focus on these two and just give you a sense of how to work with these functions. So the idea is that then we mathematically represent our impulse response as a delta of x. That's my impulse response. That's my, whoops. That's my impulse. And then this is my impulse response. Okay. And hold on just a minute. Okay, and so for example, in an X-ray system, we would have a point object. Oops, what's going on with my pen here? Point object would be my impulse, and the impulse response would simply be the X-ray image of that point object. Similarly, so the idea is, in general, we don't really care. I mean, our object is not going to be an impulse response. It's going to be some function f of x. And we'd like to see what the output is, g of x. So this is some arbitrary input now. Okay. And so in the X-ray world, for example, you'd have some arbitrary object, say someone's leg or their lungs, and you want to understand how is the image of the object related to the object itself. Okay, so to do that, we need to sort of first review how do we represent signals and images. So in this class, we will talk about both discrete and continuous. Okay, continuous is sort of our approximation for how things are in the real world. If I look at, say, someone's brain here, we think of it as, you can go to finer and finer scales, and so in some sense it's continuous. And so for continuous objects, we can have something that's continuous with time, or one-dimensional space, or two dimensions of space. So for example, the 2D image, 2D object of a brain would be S of xy, and let's say this is a time signal, say representing some time-varying signal like your voice, that would be S of t. Now, so typically for this class, we'll assume that things in the real world exist as continuous objects. And then what we actually do, though, is we want to, everything we do to create our images, certainly now in this day and age where everything is digital, is we need to then convert those into discrete arrays of numbers. So for example, on your computer screen, you may have 2000 versus 2000 voxels. And so you can assign an integer value to every voxel. So therefore, we have integer values. For example, a 1D signal, we could say that these are its values at integer values 1, 2, 3, 4, 5. Similarly, for a 2D object, we have integer values, say 1 and 2, 1 and 2. And so you have these discrete integer coordinates for every value of your signal or your image. Okay, so the next function we're going to represent is the Kronecker delta function. And so this is actually the simplest thing to think about before we go to the Dirac delta function. And the idea is that this is simply discrete. So when we have discrete things, we'll typically use brackets. And so delta of n equals 1 for n equals 0 and 0 otherwise. So this is what it looks like. And then this is very important. One of the things you do want to get familiar with is what does a shifted impulse response look like? Okay, so basically you can see this takes on value at n equals 2. And simply, if you're ever confused, just say, when does the argument n minus 2 equal 0? Well, that happens at n equals 2. Okay. Since you're seeing when does this argument equal 0? Okay. And so we want to have both the Kronecker delta function and also shifted versions of the Kronecker delta function. Okay, and then similarly in 2D, we can define delta m and n, m comma n as 1 at the origin and 0 otherwise. And so this is what it looks like. This is the Kronecker delta. And as before, we want shifted versions. So this is the m-axis. This is the n-axis. So here, obviously the peak happens at m equals 2, n equals 0. So that's shifted over on the m-axis. Here, the peak occurs at m equals 2, n equals 2 is the peak. And here, m equals 0, n equals 2. Okay. So you can imagine we have this sort of object, which is just represents something at the origin, and then we shift it around, and shifted versions just allow us to place our voxel at any place in space that we want. Okay, so why is this useful? Well, it's sort of the building blocks we need for what's called the discrete signal expansion. And so let's say I just drew this signal here, g of n, okay? And let's say it had value 1, -1, 2, okay? And this was at n equals 0, n equals 1, n equals 2, okay? So the contention is, well, g of n, I can write as 1 times Kronecker delta n -1 times a shifted Kronecker delta plus 2 times shifted even more. Okay? So this is just sort of a discrete signal expansion, which sort of has this form, where these are the coefficients, 1, -1, and 2, and these are my shifted Kronecker delta functions. And as we'll see, we can do the same thing in 2D. Okay, so actually that's, I forgot I had drawn that, so that's, I guess it was 1.5, not 2, but that doesn't matter too much. So let's actually just fix that, 1.5, 1.5. Okay, so it at least matches what's in the notes, all right? So the basic idea is any function, no matter how complicated, you can just write up as a sum of weight times shifted delta functions. Okay. Any questions up to now? All right. So similarly for a 2D signal, so this is a very simple 2x2 signal. A, B, C, D can be written as a sum of 4 simpler signals, images, where each image only has one voxel that has a value in it. And so we can sort of write that. I think here we switched the A, B, C, and D. Sorry about that. But the idea is here, let's say we're drawing this as M and N coordinates, right? So this is certainly A at delta, A times delta M, N. So that's at the origin, say 0, 0. And then plus B, and we've shifted it over by 1 on the M, so it's delta -1. Oops, let's see, I think this is wrong. And this should be M -1N, and this should be N -1, okay? Plus C times delta, I'm sorry. Let's see, where's my eraser there? How come I can't get my menu here? Oh, there we go. Let's erase that. Go back to a different color maybe. Okay, so this is M -1N plus C times M N -1 plus D times delta M -1 N -1. Okay, so the main thing is we just basically have, once again, a sum. Each of these elements, each of these images is just a shifted delta function, and we just multiply each one by the appropriate weight. Okay, so that's all you really need to know about signal decomposition, that it's really just expressing a signal as a weighted sum of shifted impulse responses. So these are the weights, and these are the shifted impulse responses. Okay, so here's another example, and let's say this is M and N, and this is 0, and let's say this is 0 here, right? So yeah, so let's draw out some of this. So let's say this is some image. We'll call it G of M N. And let's write out just the first few terms. So at the origin, right, we have 7 times the Kronecker delta. And then let's say the 8 is shifted over by 1 on the m-axis. And then the 5 is shifted over -1 and minus 1 on both axes. And then let's say the 3 is shifted over delta m plus 1 and -1, okay? And so on and so forth. So the only thing about this is just, if you're trying to understand this, just make sure you understand why, for example, this is m plus 1 and -1, okay? So the level of math in this course is not, we're not going to do super lots of math, but you do need to be comfortable with shifting signals around in space to have an easier time of this. All right. Okay, and then we have the Dirac delta function, which is defined as follows. It's 0 when x is not equal to 0, and it has this, even though it's 0 basically everywhere, it has the key, which is its area equals 1. Okay. So we can define that. We can think of this as this function here, if you remember from class, is equal to rect of x. Okay, which is also, we can also denote it as that symbol sometimes used for rect of x. And we can think of this as we reduce the width of rect of x, but keep the area of 1, then that's just basically, if the width is tau, it's 1 over tau rect of x over tau, okay? And so you can imagine the impulse response is the limit as you make these rect functions get narrower and narrower, and yet the area stays equal to 1. So that's a way you can think about the Dirac delta function, just very, very narrow rect functions that have the property that the area is equal to 1. Same thing with a 2D Dirac delta function. It's 0 everywhere except at the origin. And it also has an area of 1. And you can think of these as, this is 2 dimensions, so this is x and y, okay? And the height of it, as the base of it gets narrow, the height gets bigger, so the area is equal to 1. And so that's what you can think of as a 2D Dirac delta function. And then the limit, it essentially just becomes a spike in the xy plane. And a useful fact is that delta xy equals the product of 2 Dirac delta functions. Okay, the next thing we want to discuss very briefly is the fact that Dirac delta functions are not ordinary functions because they actually don't really have any value at any point in time. So they're actually defined, you always have to use Dirac delta functions typically underneath an integral, and the bottom line is you see what they do under an integral. So the most important property of a Dirac delta function for this class is what's called the shifting property. And that means if I take any function g of x and I multiply it by a shifted Dirac delta function, that just picks out the value of g at that location. Okay, so let's say this is g of x. I multiply it by delta x minus x naught, and then I integrate over that little thing, and that's going to give me g of x naught. All right, so basically saying this area here in the limit where that base gets very small is just going to tell me what is the value of my function at that location. Okay, so the shifting property is sort of a very important property. A useful fact, you don't need to understand the proof, is just that sometimes we'll use delta of ax, and this just is equal to 1 over a times delta x. So that just means like delta AX acts like the Dirac delta function, and it's just multiplied by this factor here. Okay, so now we can sort of, so with the Kronecker delta, it was very easy. We could just sort of say that, we had the sum of shifted delta functions at integer values. We extend that intuition to continuous space, where we say, well, if I continuous function g of x, then essentially I can still have my weights here. And then each of these is like this little triangle here, okay? And then I just look at the limit as those bases go to 0. And in that case, I get this summation sign becomes an integral sign. And so now these are my weights, and these are my shifted Dirac delta functions, okay? So instead of triangle, those rectangles essentially become these Dirac delta functions. And so you're essentially trying to, you're saying my signal can be represented by all these little Dirac delta functions weighted appropriately. Okay. And so that's the intuition behind how you represent a 1D signal. Same thing goes on in 2D. Basically, any 2D signal, for example, this surface here, you can represent as all these little rectangles, and in the limit as those rectangles become infinitely narrow, then you can represent any 2D surface that you want. Okay, so if there's any questions, just put them in the chat. Otherwise, I'm just going to keep going if there's no questions. So if you have any questions, now is a good time to ask them. So either raise your hand or put something in the chat. Otherwise, we will just keep going. All right, so the impulse response is essentially L is where L is our system. Okay, and it's basically saying if I put my delta function into my system, then this is its impulse response. Okay, so for example, my input coordinates might be something like x1 and y1. And now my impulse is, this is my delta x minus zeta, x minus eta. So my impulse is located there. My output coordinates might be different, x2, y2. For example, in X-rays, right, the object is here, it has some coordinates, and the X-ray film was over here. It's got a different set of coordinate systems. So we sort of have to keep track of two coordinate systems. So the impulse response basically depends on both where the input was in the original space, so location of impulse in x1, y1 space, and this is my output space. Okay, so that's just the notation there. So now we're going to start building up our intuition of how to deal with these things. So up to now, we've really just been doing a lot of definitions. And now we're going to do our first principle and then get a sense of what people think of this. So this is a concept you might have heard of. For example, in linear algebra, linearity is talked about a lot. So just to remind you, linearity has two properties. The first property is the scaling property. So that means if I take some image I sub 1 and I put it through my system R, and it gives me some K sub 1, so that's the transformation from I sub 1 to K sub 1. Now I multiply my image by some scalar, A sub 1, so that's just a number. If this system is linear, then the output is just the original output multiplied by that same scalar. Okay, so that's scaling. It basically means, for example, if I put in an input and get an output, now I double my input, I'm going to get double the output. So that's scaling. Addition is simply, if I put in an image I sub 1 and I get out K sub 1, and now I come back and put in an image I sub 2 and get out K sub 2, and I ask, well, what happens if I put in an image that's the sum I sub 1 plus I sub 2? Then if it satisfies addition, then the output must be k sub 1 plus k sub 2. So I have an imaging system. I image one object, I get some output. I image another object, I get some output. I put both objects there, and I image them both at the same time. Then the image has to be the sum of the images of the individual objects, if it's a linear system. So this is just another view of this. So the scalar rule is simply here I've increased my output by some factor k, and I also increase the output by that same factor of k. Here I have two inputs, 1 and 2. Now I have the sum of the inputs, and so the output is now the sum of the individual outputs. Okay, so these get added together. It's giving you my output. So if a system satisfies those properties, then it is called a linear system. Okay, so just to summarize, the system is linear if it satisfies both scaling and addition. And that means that if I have any arbitrary input where I have some scalar a sub 1 times I sub 1 plus some a sub 2 times I sub 2, then the output must be a sub 1 times my first image plus a sub 2 times my second image. So essentially, a weighted sum of inputs gives you a weighted sum of outputs. Okay, so this is really, whoops. So this is the key thing about linear system. Okay, so let's do a few examples so you guys can try an exercise. So what we're going to do here is look at problem A, and I'm going to open up a poll for this. Let's see, yeah, launch. Okay, so basically take a look at this, and this is anonymous, so you don't have to worry about it, but just take a few minutes and look and see if you think A is a linear system or not. Okay, I think most people have responded. I think, yeah, maybe there's one person who hasn't responded, but let's go forward. So it looks like of the people who responded, 75% of you said yes, it is linear, and 25% said no. So let's take a look and see how we would test that. Okay, so let's first of all look at the scaling property, and so there are some problems on the homework that was just posted about linear systems. And so if you have questions, feel free to ask now, or certainly in TA office hours or, instructor office hours, you can follow up. But let's look at scaling. So we know that G goes to G plus 10, right? Okay. So what happens if I put in 2G? Well, if I put in 2G, my output, according to that diagram, is 2G plus 10, right? But if the system is linear, then I expected to get, this is the output for, so this is a G. I should have gotten 2 times G plus 10, right? Equals 2G plus 20. And these two things are not equal. So that doesn't satisfy scaling. Okay, let's see if it satisfies addition. So we know G, so let's say addition. Let's say if G goes to G plus 10. Let's say I have another input H that goes to H plus 10. Let's say I put in input G plus H. Well, that will go to G plus H plus 10. Now we asked, does that equal the sum of these two? And that does not equal the sum of G plus H plus 20. So it also doesn't satisfy addition. So it's like, no, this is not a linear system. Okay. So any questions on that? So this is an important concept to know so that, let's see. Okay. All right, so let's go on to B. So now the question is B a linear system? Okay, so let's take a look at this. It looks like of those of you responded, 86% said yes, or 88%, and 13% said no. So overwhelmingly, people are saying it is linear. So let's just double check. So scaling, G goes to 10G, right? So that means 2G would go to 20G, right? And then if I take 10G and multiply by 2, that equals 20G. So that it satisfies that. Addition, let's look at addition. G goes to 10G, H goes to 10H, G plus H goes to 10G plus H, which equals 10G plus 10H. So that also satisfies addition. So that is linear. So that's good. Okay. So multiplying by a scalar is definitely a linear system. So that's good to know. But adding a scalar makes a system that it does not satisfy a linear system definition. Okay, the last one is this one. So now we have my object is shifted up and to the right by 1. So the question is this a linear system? Okay, so it looks like about, yeah, 63% said yes, 38% said no. So let's take a look at this. So let's first look at scaling. Okay. So here it might be, whoops. Let's think about sort of X and Y like this, right? And let's say I have an object that's there. And this says I'm going to move my object over here, right? I'm just translating my object in space. So now if I multiply my object and make it twice as big, right? Then that same object will be moved over like there. And that shifted object that's twice as big is equal to the original object multiplied by 2. Okay, so that satisfies the scaling property, right? So if I have an object and I move it, and then I make that object twice as big and move that object, then that second object is also the original object multiplied by 2. So that does satisfy scaling. Let's look at addition. So once again, let's say I have an object and I move it. Okay. And let's say I have another object out here and I move it like that. Okay. So that's just starting up at some other place in the XY space. And then let's say I had both objects at the same time. Okay. And I moved both at the same time. Well, that would still translate the thing made of two objects, translating that is the same as taking one object at a time and translating it. So it also satisfies addition, right? So that's good because so that's nice because in our daily world, we have objects that can move around in space, and the fact that that's a linear operation means that we can now apply all the engineering and the math of linear systems to objects that move around in space. And so that's good. All right. If that wasn't the case, then things would be much more difficult for us. Okay, so any questions on what a linear system is? These are just, if you understand these examples, hopefully the homework will be a little more accessible to you. Okay, the next thing we're going to talk about is superposition, and this is mostly just math. So let me just walk you through it, and the math is not so important as the idea. The idea is I'm describing some input as this is my input signal. And that's just a weighted sum, right? Of shifted Kronecker delta functions. Okay, so that's all we talked about before. And then all I'm saying is my impulse response is I assume I know the response of my system L to each of those Kronecker delta functions. Okay. So then that means that if I want to look at my output, I can say that I want to know what L of G of M is now. Okay, so that's the question. What is the linear response input? What is the linear response output when I put my arbitrary function G of M in? Okay, so that's the big question. So let's look at the answer here. So here we have it here. So basically I want my linear system applied to my input. So the first thing I can do is I can just rewrite my input as this weighted sum. All right. And then I can now use the addition property. So the response to a sum is the sum of the responses. And then I can use a scaling property. The response to a scaled version is a scaled version of the output. And then that allows me to rewrite my output as just the sum of weighted. So now these are my weights. And these are my impulse responses. Okay. And notice here I have this M prime because remember we said the input and output coordinates can be different. So this is sort of the location of my input. And M prime is the location of my output. And so right now it's just saying that if I know all of these h's, right, if I know for every set of input and output coordinates what the impulse response is, then for any arbitrary input, if I know the weight to that input, I can tell you what the output is. All right, so that's superposition. We can do the same thing in 2D and with integrals. This is the same thing where now my input is a weighted sum. These are the weights. And these are the shifted impulses. And superposition says I can use these same weights and multiply by the impulse responses to get my output. Okay, so that means as long as I know these impulse responses, then given any arbitrary input, which is set by the weights, I can tell you what my output will be. Okay, so that's a very powerful property, superposition, if it is a linear system. So this assumes linear system. Okay. Okay, so now the next property we want to get into is shift or space invariance. And so this is now an additional criteria that we're going to add to make things, our life, even easier. So previously we said, well, we had to know the input coordinates and the output, right? This is the input location, and this is the output. But now we're going to take this very special form, which is my impulse response only depends on the relative difference of the input and output. Okay, so what does that mean in practical terms? It means if I have an impulse here and it gives me this output here, okay, then let's say I shift my impulse to here, right? Now this is my impulse. Then the output must be shifted. Whoops, sorry. The output is just shifted by the same amount, but it doesn't change the response. It's just the response is just shifted. Okay, so that's space invariance. It says even if I move my impulse around, the output is the same. It's just a shifted version of the output. So that's space invariance. In the time domain, you could say if I hit my system with an impulse and I observe this output, and then I come back later in time, let's say an hour later, and hit it again, I'll get that same output, just shifted by an hour. So that's shift invariance. All right. So that's typically a pretty good approximation for a lot of systems we see in the world. For example, if I have a bell and I hit it today, and I come back tomorrow and hit it exactly the same way tomorrow, I would expect in the ideal world that it would ring exactly the same. Now, obviously, in the practical world, it won't be exactly the same because the temperature will be different or the air pressure will be different. So it'll probably be slightly different, but a good approximation is to first order, it will act exactly the same way. Okay. So this is very powerful because it means now that I only need to know one impulse response. I don't have to keep track of lots and lots of different impulse responses. As long as I know one impulse response, I'm fine. So imagine this is the input to my system, okay? Well, I can say, well, and this impulse response is the response to my first impulse, okay? So I can draw it like that. Now my second impulse comes along and it's twice as big. So I would expect if it's linear, the response will be twice as big. And since it's shift invariant, it's just a shifted version. So I get that. And then my last impulse comes in. It's the same height as my first impulse. So the response should have the same height as the first response. But now it's shifted in time by 2. So it looks like that. And then the output would then be, I would have to sort of sum over all these things to get my final output. Okay, so the output would be the sum of all those weighted and shifted impulse responses. All right, so we've used linearity, right? We used the addition property to sum up the responses. We used the scaling property to scale the responses. And then we use shift invariance to say that the shape of that response doesn't vary even as I vary where the input is located. So that's a very important property for that we will assume. And what we try to do in the real world is we try to make our systems as much as possible linear and shift invariant, such that it makes our life easier. Now, with advances in medical imaging, such with deep learning, that may become less important because then the system can learn all the nonlinearities and all the shift invariants. But for most of medical imaging, at least for now, this is still a very strong assumption. And usually, if you can make your system so it approximate this, then just the analysis is much easier. So it's generally not a bad place to start. Okay, so then what this means is we're going to introduce this concept of convolution. And once again, we're just going to walk through the math. So this is, once again, remember, this is my input, right? And these are the weights, right? And these are the shifted impulse responses. Okay, so we saw that before. And we want to put that, and we say that now my impulse response, the response of L to any shifted any shifted delta function is just now has this very simple form. That's just a shifted version of one impulse response. So now I only need one. There's only one impulse response because even as I shift my input, I can just take that impulse response and move it around. So the question is now, what happens when we put G of M into my linear system? So let's look at the math for that. Okay, whoops. So yeah, I should animate this next time, but let's just break it up. So this is saying, this is my input, and I put it into my system. Okay. This is just substitution, right? I'm just substituting in the weighted sum. Here I'm applying addition property, right? I can break the response to the sum is the sum of the responses. Here I'm applying scaling. Okay. And finally, here is where I apply shift invariance. So you notice each of these is just H with a different shift, shifted by 0, shifted by 1, shifted by 2. So now this allows me to write it as these weights, and then the shifted, this is my impulse response. With these shifts. Okay, so now this is what we call a convolution sum. And all it means is that if I can express my input as a sum of weighted delta functions, then my output is just going to be a sum of weighted impulse responses, where the impulse responses are all shifted versions of the same function. Okay, and if that's true, then we have this thing called convolution or convolution sum. Okay, so let's take a look at, we're not going to spend a lot of time doing lots of complicated convolutions in this class, but there are some important properties that you should know. So first of all, the way we define convolution, we write it as G of X star or asterisk H of X. So that's G convolved with H. Okay. Probably one of the most useful things you can remember in this class, so this extremely useful fact, is that I take G of X and convolve it with a shifted Dirac delta function, and that just shifts my function. That's great. We have an operator now. We have a mathematical representation of what it means to shift a function. So you can think of this as like a shifting operator, right? Shift. Okay. So if I have any function I want to shift it, I know I can just convolve it with a shifted Dirac delta function. So in terms of the math, I mean, if you did electrical engineering, you probably did a lot of this where we look at this form of the convolution integral, and you can see there's a multiply here. Well, first you take the h function x and you flip it. That's the minus sign, right? The flipping is the minus sign, and the shifting is that x, okay? And you multiply them together, and then you integrate the product. And so those are the 3 steps. Okay, so just for completeness, I'm going to go through that for a very simple example. We're not in your homework. There is something where you have to evaluate it, a convolution integral. The key is you'll find that a hint is that when you're doing that problem, I think I forget which is probably 2.12 or something. I forget. There's one where you have to evaluate a convolution integral, 2D convolution integral. The key is that you shouldn't, if you find yourself doing any messy algebra, then you would want to stop. It's actually, if you just look at symmetries and known facts, it's actually quite straightforward, the solution. So the solution doesn't require a lot of messy algebra. Okay, so that's, yes, question?
Yeah, I have a question. Can you explain again what you mean by flip? What are you flipping there?
Yeah, so I'll show you an example in a minute because it's not obvious. And I wouldn't worry about this too much. This is just more, we're not going to use too much of this in the class, but just for completeness, this is going to be important. The thing we're going to use the more important thing for the class is this fact of shifting or convolving with delta functions, okay? But let's go through an example just for completeness, since it might be useful for other things, other classes you take. So first, we're going to do a more simple example just to get you warmed up, and then we will do the more complicated example. So here is, remember, this is my rect function, rect of x. And so if you're not familiar with rect functions, just make sure for this class, definitely be comfortable with rect functions, sinc functions, and delta functions. Those 3 things will get you through most of the class, okay? And so here we have a rect function. So let's say what we're doing. I'm taking rect of x, and I'm convolving it with what? Well, I have a delta function at -1/4 plus a delta function at x plus 3/4, right? So because that is, it's located at -3/4, so it must be, the argument must be x plus 3/4, okay? So those are the sorts of things you just need to be comfortable with, being able to look at shifted functions and being able to write down their mathematical representation. And then we apply a very useful fact. This just equals rect of x shifted by 1/4 plus rect of x plus 3/4. Okay, so that's very simple. Now, this is a very simple problem. What would be useful for you to do is what would have happened if I gave you rect of, say, x over 3? And that you might want to try that on your own. And if you're comfortable with doing things like that, then you'll have essentially a lot of the basic sort of math skills you need for this class. So we don't, the math in this class is not, any one step is not complicated, but it's building it up and knowing how to use it and applying it to medical imaging that can be tricky. So let's draw out what the solution is, okay? So remember, basically, what is it saying? Well, it's saying that this is, say, 0. So it's saying rect of x plus 3/4, okay, so, or x minus 1/4. So we know that the center of the rect is at 1/4, and we know that rect has width of 1, and it goes out 1/2 this way, so it goes 3/4 and minus 1/4. So there's a rect function like that. And this is now centered at 3/4. Okay, so it goes halfway this way, so it's here, and then it goes out here to 5/4. So it looks like that. Okay, so that's what it looks like, gap looks like. So one question is, can I rewrite this as another rect function? And that's something, that would be a good problem for you to do and make sure you're comfortable with that. Okay. So that's, so this is very important to be able to take a rect, any function, convolve it with different Dirac delta functions, and just know that you're just shifting the original function around. And if there's 2 functions, then you would basically, add up those components. Okay. So does that look correct? think that looks correct. This is minus 3/4, right? Yeah. Okay, I think that's correct. Okay, so here's the more complicated example is what do we mean by how do I take two functions continuous and now convolve the two together? And so here's where we're going to sort of look at that flip and shift and just give you a sense of how to do it, just sort of to make this for the sake of completeness. So so g of xi is my rect function. So that's my rect function. H of 0 minus xi is basically just rect at x equals 0. So this is at x equals 0. Then that's just rect of minus xi. In this case, it's not a great example because rect of minus xi is just rect of xi because rect is symmetric. So it means that now I take these two functions and I multiply them together and I get another rect function, right? So these two functions multiplied together a rect function. And now I take the area under this. So the area, if I integrate that, the area is just equal to 1. Okay. So what I would do is in my output, I say, okay, at x equals 0, I have value of 1. Now this is a shift. I've set x equals 1, right? So this is the value of x. So now this is this is essentially rect of 1 minus xi. Okay. So where does that have its middle? It has its middle at x equals 1, right? Because that's where xi minus 1 equals 0. So if I take this function and multiply by this function, they don't overlap at all. So this integral would equal 0, right? So I know at x equals 1, I have 0. Okay, that's what the convolution operation tells me to do. Now let's say this is x equals 1/2, right? Because this is the value of x, right? Now I've shifted, this is equal to rect of 0.5 minus xi, right? So now the middle of that rect function is exactly at 1/2. So these two rect functions only overlap partially. So this area now is equal to 1/2. And so I can say that x equals 1/2, the value of my convolution sum is 1/2. And if you do all the other forms, you notice it's going to basically end up something like that. Okay. So the convolution of two rect functions is what we call a triangle function. So that's sort of, if you understand this, then that should be sufficient to get you through most of this class. All right. Okay, so let's talk about 2D convolution. 2D convolution is just the same thing, but now we're doing, instead of 1D integration, we're doing 2D integration. The notation, strictly speaking, a lot of people use 2 stars, but as long as these are two-dimensional functions, then we'll sometimes just abbreviate it with 1 star, just because it's sort of obvious that it's a 2D convolution because you have two-dimensional signals. Okay, the definition is here. Now, the 2D convolution, it's much more complicated, so we typically, except for very simple examples, you're not going to do it by hand. You're going to use MATLAB, but let's look at a very simple example first that you can do by hand. So look at this. This is one function is this shifted. It's a 2D function, right? Because it's defined on the xy plane. So we have a delta function, and we also have a shifted delta function, okay? And we're going to convolve that with my two-dimensional rect function. Okay? So one of the challenges of this class is you might, from your previous classes, be used to one-dimensional functions. It does take a little bit of practice to get used to two-dimensional functions. And obviously, if we're doing images, two-dimensional functions are very important. So just know that with practice, you'll get used to that. So let's write down mathematically what this is. We know that from our properties, this should just be equal to rect. It's only going to be, this doesn't shift it at all, right? So I have rect of xy. And so I can draw, that's this part here. Okay, this is the rect of xy, right? And then I'm going to add to it the rect convolved with this one, which is going to shift things. So that's rect of x plus 1/2 y. So that's going to give me this rect function here. Okay. So this is rect of x plus 1/2 y. Okay, so basically now linearity applies, right? The value here is just 1 because they don't overlap. The value here is just 1, but where they overlap here in the middle, the value is 2. Okay, so we're seeing that, and this is a good example. Essentially, I have these two Dirac delta functions. I convolve with a rect function. The answer is just wherever there's a delta function, just put a rect there. Okay, so when you think about 2D convolution, you can just think about repeating your taking your whatever you're convolving with, and then just moving it to these different delta functions and then scaling it appropriately. Right. So that is in fact what you did with your MATLAB exercise. If we think about this, this can be represented, whoops, what's going on here? All right. This can be represented as a sum of lots of little Dirac delta functions, right? Or delta functions, right? I can imagine these are all little dots, right? And I have all these delta functions and they're just shifted. So everywhere I have a delta function, I just plop down one of these things and that just blurs out that. And then I get a sum of all these blurred components, and that's going to give me my overall thing. And if I make this blurring bigger, then now I'm going to get just bigger blurs added together. And that's going to give me that. Okay, so that's one way you can think of 2D convolution. You can just think, okay, especially this cross is a very simple object. It's just the same height everywhere. And so I just take this is my sort of blurring kernel here, and I just imagine repeating that over and over and then taking the sum of all those kernels, right? And whereas Professor, yes, go ahead, question?
Yeah, so if you look at the previous example, right, in terms of a function, if you had like we previously looked at, when you take the rectangle function and you convolve it with the delta function, you get that's the convolution, right? So what controls the blur? What in the function would sort of denote the blurring?
You mean for this example, what denotes the blurring?
Yeah.
So let's say this is x of h of y, right? So you can imagine, if we were to plot at x and y, maybe this one looks like this, right? It's some function of x and y. And then this is just some other function, but it's just it's got a bigger blur. The width, okay. So basically the width of that function, so this is your impulse response or your point spread function. So the wider it gets, the more blurring there is.
Okay, thank you.
Did I answer your question? Yeah, okay. All right, so the final few slides are just sort of for your knowledge, especially in this day and age. I mean, convolution was not something that most people had to know about, except for electrical engineers and other people. But nowadays, more and more people are actually seeing the term convolution because convolution neural networks. And it's basically just to remind you, essentially, you have the basic knowledge you need to know now. Essentially, convolution here in this case is this is what's called my convolution kernel. Okay, and so essentially what I can do is in the convolution is essentially just this is my image, and I'm multiplying it by my kernel, right? And then I do that summation, right? So I sum that up and I get the value there. And then what I would do is for the next point, I would just shift over my inputs. And so now I'd have 0, 1, 0, 1, 1, 0, 0, 1, 0. I'd multiply that by my kernel. I'd sum that up, and that would just give me the value there. Okay, so it's essentially this thing of taking that and just shifting it and multiplying it and integrating, all right? So this is another example where they actually do it for you, where they basically, you're just sort of taking this kernel and plopping it on different parts and then just moving it around. And everywhere you multiply and you integrate or sum, and then you get these outputs. So that's essentially what convolution is doing in convolution neural networks, and also in your MATLAB problem. That's also how it's evaluating it, or the fundamental mathematics. The nice thing about convolution, just to tie things up, is here I have an object. I'm convolving it with this filter, and you can sort of notice that this is sort of an edge filter. It's sort of picking out the edges of this image. And notice here, I've just shifted it, right? I've shifted it over by that. And notice the output is also shifted over by the same amount. So convolution is obviously linear. It's just multiplying and adding. And so, and it also has, you would expect that should be shift invariant. And so it is sort of interesting that the convolution is also shift invariant, which is sort of by design it will be. Okay. So that's all I have for the material I want to cover today. So what we can do now is see if there's any questions before we conclude this session.
I just have a quick logistical question regarding the textbook.
Sure.
So
Yes.
I know we were discussing the whole like opt out and opt in option, and I found it somewhere else. So I'd like to opt out of the course material, but I couldn't find where to do that. And then I went through the instructions that you have posted on Canvas, and there was no link where it said there was a link because it's a PDF. So I just wasn't
Yeah.
sure.
So did the PDF? I don't remember. Does the PDF have like an email that you can send it to?
Yes,
If
but
not,
I know I haven't
yeah.
done that yet because I thought it would be easier to just like follow the link and just click something to opt out, and I didn't know if there was a simple way to do that.
Yeah, let me look at the PDF and I'll email them. And so you basically, you clicked on the link in the PDF and it didn't go anywhere.
Yeah, I mean it's like a hyperlink, so there is no link because it's a PDF. Like there was no link present for me to click on.
Okay, let me take a look at that. If you could actually just send me an email just to let me know, and then I can forward your email to textbooks and get them to fix that.
Perfect. Thank you.
Sure. Okay, let me see. There was something in the chat here. Okay, just thank you. All right. Great. Anything else before we conclude today's session? Okay, if not, I'm going to stop the recording. And so